Hello! In this video we're going to look at example 8 from the chapter 6 review worksheet. So this question supposes that the average height of a U.S. adult female is 65 inches tall, standard deviation of 3.5 inches. And we're going to assume the distribution of female heights is normal. And we'll talk about, well, for one of these parts it's important, for another part it's actually not important at all. But we want to figure out what is the probability that a random female is greater than 5 foot 11 inches. So first thing I want to note is that 5 foot 11 inches is, you can think about like 6 feet tall would be 6 times 12 is 72. And then we're losing 1 inch from 5 foot 11, so 71 inches. All right. Okay, so then we're going to assume here mu, we're going to assume that's 65, and that the population standard deviation, sigma, we're going to assume that's 3.5. Alrighty. Okay, so if we're just taking one random person, we're going to use the normal distribution. I'm going to go here and not GeoGebra. I'm going to Google StatKey. Go into StatKey. Theoretical distributions. We're looking at the normal distribution. All right, I want to change the mean and standard deviation. We assume that mean is 65, and the standard deviation is 3.5. So mean 65, click OK. Mean 65, standard deviation 35. And we want to know what is the probability that a randomly chosen person, female, is 5 foot 11 inches or 71 inches tall. So close that. So then if we're looking, going back to StatKey, on here, the center is 65. I want to know what the odds that someone is 71 inches tall. So that's going to be right tail. I need to make this value right here 71. 7 inches tall. And the area under the curve, this red value, that's 0.043. That is the probability. All right, the probability. A randomly chosen female is over 71 inches tall is 0.043, about 4.3%. All right, what's the probability that the average height of a random sample of n equals 10 is greater than 5 foot 11? All right, so it seems like I'm asking the exact same thing. I'm not trying to be tricky. The answer is just 0.043, but no. If you think about this, the probability of getting a female who's 5'11" is fairly low, less than 5%, but definitely happens. But now we need to get a sample of 10 people. So essentially you might want to think at least half of these, the sample of females has to be over 5'11", which is a lot less likely. Or they all have to be around 5'11", and 10 of them times 4%, it's going to be a pretty small number. So I want to note right here, we still have mu equals 65. And the population standard deviation has not changed. Or sorry, 3.5, not 65, the population standard deviation. But now I have a sample size of 10. So how does that change things up? So now we need to figure out standard error. And that is equal to the standard deviation divided by the square root of sample size. All right, so we're given the standard deviation. N right here, the standard error would be the standard deviation divided by the square root. Oh, sorry, that's going to be n. So this first part, the standard error is identical to standard deviation if we have a sample of one person. But if we have a larger sample, we need to change that standard error to 3.5 divided by, and now I'm going to add on the square root of 10. All right. If you throw that in your calculator, we get this to be about 1.1068. 3.5 divided by the square root of 10. So how does that change the scenario? If I go back to stat key, I need to change the standard deviation. The mean is still the same, but now this is going to be 1.1068. To change that standard deviation, still looking at right tail. Down here, this needs to be 71 inches tall. And we get essentially 3.0 e to the minus 8. Go over here. All right, probability. Getting a sample of 10 females. Average is greater than 71 inches. That would be 0.1234567 So almost 0, but not technically 0, but highly, highly, highly unlikely. If you got a group of 10 females whose average height is 71 inches tall, I would argue that's not a random sample. You're getting 10, basketball, volleyball players, or just very tall people. So if we move up a level to say, what are the odds of getting 30 with height greater than 5'11"? Again, we have the same idea. Sorry, let me change that. We get the average is still 65. Standard deviation is still 3.5. Now the standard error is going to be 3.5 divided by the square root of 30. Standard error can get smaller, and that's about 0.639. Throw that in your calculator. So we need to use this standard error when we go back to the normal distribution. So I'm going to change this to 65 is still the mean, but now that standard deviation has decreased to 0.639. Click OK. Click on right tail, make this bottom value 71 for the cutoff. And here, it's even less likely. So we would need to have more precision to know how many decimals to go, but I'm going to say essentially 0, or statistically 0. Probability of getting a random sample of 30 females whose average height is greater than 71 inches is statistically 0. Almost impossible to get a truly random sample. So if you did, then that would be the argument that this mean cannot be correct, because this is so highly, highly, highly unlikely. All right, so just as a quick summary, right here, I didn't write this up here, but we could have written standard error is 3.5 divided by, down here, the first part of this, we're just looking at one person. So the formula still works. 3.5 divided by the square root of 1. Square root of 1 is just 1. We just end up with 3.5. And that's why we had a much higher probability of getting one person 5'11" or taller, but much, much less likely to get 10. Less likely to get 10 whose average is 5'11", and essentially impossible to get a group of 30 whose average height is greater than 5'11".